Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 12.3 entitled Geometric Sequences. And today we're going to talk about a bunch of different objectives here. We're going to talk about what geometric sequences are, as well as what the partial sum of a geometric sequence is. And then we're going to talk about an infinite geometric series as well. But we're going to start off with geometric sequences. And again, we dealt with these when we were when we were talking about section 12.1 and dealing with the topics of sequences and how you can write the function for a sequence. So remember that an arithmetic sequence, which we saw in 12.2, is when you have repeated addition, but a geometric sequence is when you have repeated multiplication. So in the equation here, they're going to have the first term being a, and then they're going to multiply it by r. And again, that's your common ratio. And then you're going to multiply by that r again, so you get r squared. And multiply by r again, so you get r cubed, and so on and so on. So the equation that we'll be using then is this one right here. And again, I like to tweak it. A sub n equals a sub 1 times r to the n minus 1. So a sub 1 is just your first term, r is your ratio, and n means any number in the sequence. So that can be a specific number you're trying to find, or it could be, as we'll see in some examples, you can determine if you have numbers that are right next to each other or if they're further away from each other. So just like we saw with the arithmetic sequences, there are some different ways that you can have these types of problems presented to you. So in this first example here, we're just going to take a look at the sequence and make sure we can identify all the different parts of it. The sequence starts with 3, and then it goes to 6, and then 12, and then 24, and 48. So hopefully you can tell that we are multiplying by 2 every single time. Okay? And you have to be multiplying by the same number in order for it to be a geometric sequence. So our first term is going to be the very first one. So a sub 1 is 3, and then your r, your common ratio, is 2. So here it says, notice that the ratio of any two consecutive terms is r equals 2. So we can start anywhere. We don't have to start with the first term. We could start here at our fourth term, but to go from the fourth term to the fifth term, you still have to multiply by 2. So then if we're going to write the equation for the nth term, that means we would take our first term, which is 3, and then multiply it by our ratio, 2, and then that ratio gets applied to the n minus 1 power. Okay, so let's try that here with this sequence, just to make sure we have the basics down. This time we're going from 2 to negative 10, and then to positive 50, and then to negative 250, and then positive 1250. So here we're going to be alternating. So that means we have to be multiplying by a negative number. If we're going from a positive to a negative, we have to be multiplying by a negative. And in this case, it's going to be 5, because 2 times 5 is 10. And that happens here from 10 to 50. We multiply by negative 5. And then multiply there again by negative 5, and so on and so on. So my first term is 2, but my ratio this time is negative 5. And here it says when r is negative, the terms of the sequence alternate. So we've seen that before with the arithmetic sequences when we were writing the equations. In section 12.1, there were some geometric ones in there, and we talked about how it's really negative 1 to the n minus 1 power. Okay? But here, if we're writing the equation for our nth term, this would be, and if you want to put a sub n equals out in front, you can. But our first term is 2, and then our ratio is negative 5. So if it's negative, put it in parentheses, and then that will be applied to the n minus 1 power. Okay, so I think we have one more of those. And this one, this sequence has fractions. And when you're going from a whole number to a fraction, some students like to think of it as a division. But remember, geometric sequences is repeated multiplication. So when you think, oh, I would divide, that really means that you're multiplying by a fraction. So here to go from 1 to 1/3, we would multiply by 1/3 or divide by 3. And then 1/3 times 1/3 would be 1/9. And 1/9 times 1/3 would be 1/27, and so on. So it's like dividing by 3, but dividing by 3 is the same as multiplying by 1/3. So hopefully you're comfortable with that concept. Okay, so our first term is going to be 1, and then our ratio is going to be 1/3. And we always want to write our ratio as a fraction, multiplying by a fraction, because we have an equation where we have to put a specific number in for the ratio. So if you are thinking in terms of dividing by 3 and you put a 3 in for the ratio, that's going to mess up your geometric sequence and the equation that you're building for it. So anytime you're thinking of dividing by a number, make sure you write it as multiplying by that fraction. So here we'll have a sub n equals 1 is my first term, and then 1/3 is my ratio, and that's going to be applied to the n minus 1 power. Okay, so now that we're comfortable with geometric sequences and the parts of them and what they mean, we can find the nth term of a geometric sequence if we know any two terms. So this is very similar to what we've done with the arithmetic sequences, except now we're multiplying. So in part A here, we're going to find the 8th term of the geometric sequence. Now this sequence isn't very long. It has the first 3 terms here, and we want to find the 8th term. So I want to start by looking at my first few terms and figuring out what my ratio is. So to go from 5 to 15, my numbers are getting bigger, so I know I'm going to be multiplying by a whole number. So I'm going to be multiplying by 3. And I check it again. 15 times 3 is definitely 45. So I could then keep multiplying by 3 until I got the 8th number. That wouldn't be very challenging. But here we want to write the equation for it so that we can find the 8th term. So I'm going to skip down to part B here, because now that I know my ratio and I have my first number, I can write my equation. A sub n equals, my first term is 5 and my ratio is 3 to the n minus 1. So it doesn't take long to write that equation. And now I can actually use that equation to help me find my 8th term. So I'll have 5 times 3 to the 8 minus 1. If I want to find my 8th term, then I'm going to plug in an 8 for the n. And you could set this equal to a sub 8 as well. Okay, so this is really 5 times 3 to the 7th. And remember, order of operations, you want to do 3 to the 7th first, and then multiply it by 5, and you should get 10,935. So when you have repeated multiplication, your numbers are going to get really big really fast. So even though this is only the 8th term in the sequence, we're already at 10,000 something. Okay? So you should be comfortable with that now, looking at a sequence, finding the ratio, writing the equation, using the equation. You should be fine with that, because we've done that for the last 3 sections now. So the next thing we're going to take a look at then is the partial sums of a geometric sequence. And a partial sum, they explain it here. And again, this is where we're just adding the terms of a geometric sequence together. So we're summing the terms. And partial means that we're going from one spot to another. Now you could take this all the way out to infinity. So we'll talk about that in the next section when we talk about infinite series. Okay, or it's coming up in these notes actually, in the next part of these notes. So, but here we're just starting with our value of 1 and we're going up to some other value, some other term. And this right here is our geometric sequence. Okay, they're using k instead of n here because our k value is 1 that we substitute in. Okay, and to find the formula for our partial sum, you actually take your sum and you multiply it by r, and then you subtract it from your original sum. So that's what they're showing here. This is your original sum, your partial sum. This is where you multiply everything by r. And notice that when you multiply everything by r, your terms kind of shift over a little bit. Your a is gone, and now you have a times r as your first term, so you're kind of shifting here. And then when you subtract them, everything cancels out except your first term and your last term. So that's what we're going to use then to complete our equation. Okay, so we're actually going to have this right down here as our equation. So our partial sum for a geometric sequence is going to be a, and remember that's really a sub 1, times 1 minus r to the n over 1 minus r. And again, r is your common ratio, n is the term you're trying to find, and remember that that a is really your first term, a sub 1. Okay, so let's see if we can do that then. Let's find the sum of the first 5 terms of the geometric sequence, and the sequence starts at 1, and then we have 0.07, and then 0.49, and 0.343. So we've got the first 4 terms, we need the 5th term. And notice that we're going from 1 to 0.07, so I'm multiplying by 0.7. And then there again, I'm multiplying by 0.7 and times 0.7. So if I multiply again by 0.7, I'll get 0.2401 as my 5th term. Okay? And then I want to find the sum of those 5 terms. Now again, this isn't super duper challenging here. I've got my 5 terms already, so if I wanted, I could just add them up. Okay, but let's practice that formula. Okay, so let's rewrite it from the previous slide. We had our partial sum, and it was equal to that first term times 1 minus your rate to the nth power, or your ratio, over 1 minus your ratio. Okay, so I know my first term is 1, so that's easy to substitute in. And then I have 1 minus my ratio is 0.7 to the n, so that's going to be to the 5th power. So I'm taking 0.7 to the 5th power over 1 minus 0.7. So now it's just a calculator problem. So I'm really going to take this 0.7 to the 5th power and then subtract it from 1. When you do that, you should get 0.83193. And then here in the denominator, 1 minus 0.7 is going to be 0.3. So when you divide those, you should get 2.7731. And again, I'd have to multiply everything by 1, but that doesn't really do anything to my partial sum. Okay, so you'll see problems in your homework where they want you to find the sum of a geometric sequence. So use the equation. You might have to find the other parts of the sequence as well. You might have to find the other terms. So you might need to know that. But for this equation, actually, we don't. We just need to know the number, and we need to know the ratio, and we need to know our first term. So if they wanted to be really tricky in your homework, they could give you the first, they could give you a part of a sum, but not the first term. So you might have to work backwards and find that sequence. You might have to find the first term in the sequence. So they could give you maybe the 9th term to the 19th term, and then you'd have to work backwards to find the very first term. Okay. All right, so now we have to talk about an infinite series, and this is our last couple of concepts here. And an infinite series just means that we are going to be adding everything up to infinity. So we're going to add our first term, our second term, our third term, and so on, all the way up to infinity. So you'll notice at the top of your summation notation there, you have the infinity symbol. Now what this means is as n gets larger and larger, we keep adding more and more terms. So as n gets larger, that sum, that partial sum, is going to get closer and closer to the sum of the series. And then they do a lot of explanation here for some other terms that we're going to be seeing, but the explanation here gets a little wordy, but the summation that they have at the very end is very nice, and it just boils it all down to what you need to know. But basically, as we're summing our numbers, as the sum is getting closer and closer to 1, that means that your number of your terms is getting closer and closer to infinity. So when that happens, if you keep adding up your terms as you're going to infinity and your sum gets closer and closer and closer to 1, that means that it is converging or it is convergent. Okay? And if it doesn't do that, then we say it's divergent, just like the book. Okay? So those are two terms that we're going to be dealing with. And again, they summarize this in the next couple of slides here. And we can talk about an infinite sum and we can talk about an infinite geometric series as well. So an infinite geometric series then is where you're taking a geometric sequence and you're adding up all of the terms. So we're going to be starting with our first term and going all the way to infinity. And really we're going to be using that same equation as our partial sum. So again, this equation's on your little formula sheet, and the infinite the infinite one is going to be similar to that. It comes from this, okay? And again, we want to try and get our ratio here, the absolute value of our ratio. It can be shown that if the ratio is less than 1, meaning that it's a fraction or a decimal, then r to the nth power, as we keep putting more and more terms into this, we're going to get closer and closer and closer and closer to 0. And you can double check that and play around with that if you want on your calculator. You could pick some decimal and keep raising it to bigger and bigger and bigger powers and adding, but we're going to end up getting closer to 0. So what this all boils down to here is that as the number of terms goes to infinity, the sum, the partial sum, ends up getting closer to a over 1 minus r. So that's where this is coming from here. So we have our infinite geometric sequence, or infinite geometric series is going to look like this. We've got our sum, I've got our summation notation with our sigma, we have k equals 1, and we have infinity, and then we have our geometric sequence there, a times r to the k minus 1. Okay? And it says that if r is less than 1, then the infinite geometric series converges and has a sum that can be defined this way. So when that ratio is less than 1, well, the absolute value of the ratio is less than 1, then that tells us that we can actually find the sum using this formula. If our ratio is, or the absolute value of our ratio is greater than or equal to 1, then the series is divergent and we can't find its sum. Okay, so when we're dealing with the infinite geometric series and the sum, the partial sum of it, we have to know that ratio. The absolute value of the ratio is really important because it tells us if it converges or if it diverges. If it converges, then we can find its partial sum. If not, if the geometric sequence diverges, then we can't find its sum. Okay, so let's take a look at an actual example so we can see the difference here. We'll do one of each type. So here we want to determine if the geometric series is convergent or divergent, and then if it is convergent, find its sum. Okay. So for part A here, we're starting with 2, and then we're going to 2/5, and then 2 over 25, and then 2 over 125. So the numerators are all 2 here, but our denominators are really multiplying by 5. So that means to go from 2 to 2/5, we're multiplying by 1/5. And then we would do the same. We're multiplying in the numerator by 1, multiplying in the denominator by 5. So we're multiplying the whole thing by 1/5. And again there. Okay. So then my ratio there, the absolute variable, or the absolute value of that ratio, 1/5, is going to be less than 1. So this means we're convergent. And that means I can find my sum. So now I'm going to use that equation. That was right here. The S equals A over 1 minus R. Remember this A is A sub 1. So then to find my sum, my first term is 2. And then it was 1 minus my ratio, which was 1/5. So that's really 2 over 4/5. And then I would multiply by the reciprocal, get rid of that fraction within the fraction. So those are going to cancel. So I really have 2 over 1 times 5 over 4 if you're thinking of it mentally. So that's going to be 10 over 4. And you could reduce that to 2.5 if you want to write it as a decimal, or 2 1/2 if you want to write it as a fraction. That's fine as well. Okay, so if I kept adding up the sum, notice that the terms are getting smaller and smaller. They're getting closer and closer to 0. So they're going to converge. Okay? But if I added all of them up from here to infinity, I would get 2.5. Okay, so let's take a look at part B. My first term is 1. My next term is 7/5. Oh, and then they have it written nicely with the exponents here. I've got 7/5 squared, 7/5 to the third. So that's really easy to tell what we're multiplying by. We're multiplying by 7/5 every single time. Okay, and the absolute value of 7/5. Okay, this is just the absolute value, just gets rid of the negatives. You know that. This, though, however, is greater than or equal to 1. 7/5 is greater than 1. So this means we are divergent. Okay, so that means we have no sum. So we can't actually find our sum there. Okay, so again, if the common ratio is less than, or the absolute value of the common ratio is less than 1, then it converges and we can find our sum. If the common ratio is greater than or equal to 1, the absolute value of it is greater than or equal to 1, then it's divergent. Okay? So take a look at this homework. And part of the homework, you're doing 5 through 61 every fourth. So you do the first problem, skip the next 3. Do the next one, skip the next 3. Okay? And there's a lot of formulas and there's a lot of terminology. So work on these problems, check the odd ones in the back of the book, and if you have any issues, come on in and see me before school.